Please subscribe to support the channel. The question that has fascinated scientists for centuries is this: why is the speed of light the ultimate speed limit in the universe? It sounds simple at first. We know light is fast, so fast that in a single second it can travel around the Earth more than 7 times. But why should there be a limit at all? Why can't something just go faster if we give it enough energy, enough fuel, or enough force? This question is not just about physics. It touches the very fabric of reality. If you peel back the layers, you discover that the universe is not built like an open racetrack where you can endlessly accelerate. Instead, the universe is structured with boundaries written into the laws of nature itself, and the speed of light is at the heart of those boundaries. When we say nothing can go faster than light, it almost feels like a cosmic rule handed down without explanation, but science doesn't work that way. This isn't just an arbitrary number the universe decided on. It's the product of deep physical laws that define space, time, energy, and causality, the sequence of cause and effect itself. Understanding why this speed is absolute requires us to look at history, at theory, at mathematics, and even at the very limits of imagination. The mystery grows even more intriguing when you realize that this speed limit isn't just about light itself. It's about the maximum rate at which information, influence, or interaction can move from one place to another. In other words, the speed of light isn't only about photons darting through empty space, it's about the architecture of reality. If you could somehow outrun light, you wouldn't just be breaking a traffic law of the universe. You'd be tearing apart the fabric of space-time and unraveling cause and effect. That's what makes the question so fascinating. It's not only about speed, it's about everything we know and experience. Why does your phone's GPS rely on the constancy of light speed? Why does the sun shine in the way it does, with nuclear reactions constrained by these laws? Why do the most advanced scientific instruments, from particle accelerators to gravitational wave detectors, keep confirming this limit? The answer to all of these traces back to that one profound question: why is the speed of light the ultimate speed limit? The journey to answer this is one of the most thrilling adventures in human thought. It's not just about physics equations, it's about challenging our intuition, rethinking how the universe behaves, and recognizing that reality is stranger, deeper, and more interconnected than our everyday senses suggest. To move forward from the question itself, we need to get clear on what we actually mean when we say the speed of light. Numbers are thrown around so casually that it can almost dull their significance, but this number is one of the most profound constants in the universe, about 299,792 kilometers per second. To put that into perspective, that's nearly 300,000 kilometers in the blink of an eye. In more familiar terms, that's roughly 186,000 miles per second. If you wanted to compare it to human scales, think of it like this: if you could somehow build a car that went at the speed of light, you could go from New York to Los Angeles in less than the time it takes to snap your fingers. You could travel from the Earth to the Moon in just over a second. And in a little more than 8 minutes, you could cover the 150 million kilometers between Earth and the Sun. But the important thing is not just how fast light is, it's the fact that this speed is constant. When scientists say the speed of light is a universal constant, they mean it in a very deep way. Light in a vacuum, meaning in empty space, without air, water, or any other medium slowing it down, always travels at exactly that speed. It doesn't matter if you're on Earth, orbiting another star, or drifting in the emptiest voids of intergalactic space. If you measure it carefully, you will always find the same number: 299,792 kilometers per second. Now that might sound ordinary at first. Sure, light moves fast, why wouldn't it be consistent? But here's where things get mind-bending. When you think about most other things in physics, speed is relative. If you're sitting in a car going 60 kilometers an hour and another car passes you at 80 kilometers an hour, from your point of view that other car is only going 20 kilometers an hour faster than you. Speeds add up and subtract depending on your perspective. That's how we experience the world. But light doesn't behave that way. No matter how fast you are moving, if you measure the speed of light, you will still measure it as exactly the same value. Even if you're racing toward a beam of light at half its speed, it doesn't appear doubled. It still comes at you at that same 299,792 kilometers per second. And if you're moving away from it, it doesn't get slower. Light plays by different rules. This is one of the deepest mysteries of nature. The universe seems to have embedded this speed into its very bones, not just as a limit for light itself but as a foundation for the laws of physics. It is so central that scientists often refer to it with a simple letter, c. The c doesn't stand for light in English. It comes from the Latin word celeritas, meaning swiftness or speed. And once you start to see how this constant shows up in equations, from Maxwell's equations of electromagnetism to Einstein's relativity, you begin to understand that c is not just the speed of light. It's the speed of causality, the maximum pace at which the universe allows events to be linked across space. When you look closer, you realize that light itself is almost incidental here. Photons, the particles of light, happen to be the most obvious carriers of this speed limit because they have no rest mass. But the constancy of this speed goes deeper. It's embedded in the structure of space and time themselves. In fact, many physicists argue that if we had never discovered light at all, the mathematics of spacetime would still force us to conclude that there must be a universal speed limit, and its value would still be what we call the speed of light. Think about what that means for how the universe operates. If information, energy, or influence could travel faster than this speed, then cause and effect would lose their meaning. Signals could arrive before they were sent. Events could ripple backward in time as well as forward. The neat order we rely on, the idea that a cause produces an effect in sequence, would collapse. The constancy of the speed of light is what keeps the universe coherent and logical. Even though this number has become famous today, it wasn't always known. There was a time when people argued about whether light moved instantaneously, appearing everywhere at once, or whether it took time to cross space. Some philosophers believed it must be instantaneous because our eyes seem to catch light without delay. It was only through centuries of careful observation and experiment that scientists came to pin down the fact that light moves at a finite, measurable, and constant speed. And here's where our journey naturally transitions, because to appreciate why this number matters, you need to understand the history of how humanity uncovered it. From astronomers in the 17th century watching the moons of Jupiter, to James Clerk Maxwell unifying electricity and magnetism in the 19th century, to Einstein's radical leap in the early 20th century, each step brought us closer to realizing that this wasn't just a speed, it was the speed, the ceiling, the defining pace of reality. When we talk about the speed of light as the universal speed limit, it can feel like such a solid, obvious fact that we sometimes forget it was not always known. In fact, the path to discovering the true nature of light and its speed was long, full of debates, wrong turns, and brilliant breakthroughs. To appreciate why the number 299,792 kilometers per second carries so much weight, we have to go back in time and trace the history of how humanity gradually uncovered this truth. The story is as much about persistence and imagination as it is about science itself. For much of human history, people assumed light must travel instantly. When you look up at the night sky, the stars appear to shine into your eyes without delay. When you light a candle or strike a match, the glow seems immediate. Early Greek philosophers such as Aristotle believed light was instantaneous. Even great minds like Descartes in the 17th century argued against the idea of a finite speed, partly because no delay in vision could be detected with the naked eye. Yet beneath these assumptions lay the possibility that light was not infinite in speed but merely incredibly fast, so fast that ordinary human perception could never catch its delay. The first decisive evidence came from a Danish astronomer named Ole Armer in 1676. He was observing Io, one of Jupiter's moons, and noticed something peculiar. The timing of Io's eclipses, when the moon passed into Jupiter's shadow, seemed to shift depending on the Earth's position in its orbit. When Earth was moving away from Jupiter, the eclipses seemed to happen later than expected. When Earth was moving toward Jupiter, they appeared earlier. Armer reasoned that this discrepancy wasn't because Io itself was irregular but because light from Io was taking longer or shorter to reach Earth depending on the planet's distance from Jupiter. By carefully studying these differences, he made the first real estimate of the speed of light, putting it at around 220,000 kilometers per second. His value wasn't perfect, but the insight was revolutionary. Light was not instantaneous, it had a finite speed. After Armer, other scientists refined the measurements. In 1728, the English astronomer James Bradley discovered the phenomenon of stellar aberration, in which the apparent position of stars shifts slightly due to the Earth's motion combined with the finite speed of light. This effect gave another confirmation that light travels at a finite, measurable velocity. By the 19th century, experiments on Earth provided even more precision. Hippolyte Fizeau in 1849 used a clever device involving a rapidly rotating toothed wheel and a beam of light reflected by a distant mirror. By adjusting the speed of the wheel until the reflected light was blocked, he could calculate how fast light traveled. His result, about 313,000 kilometers per second, was remarkably close to the modern value. Léon Foucault later improved the method using rotating mirrors instead of wheels, narrowing in further on the true figure. Yet even as the speed was being nailed down experimentally, the deeper nature of light remained mysterious. Was light a stream of particles, as Newton believed, or a wave, as others argued? This debate dominated physics for centuries. The wave theory gained strength in the early 1800s thanks to Thomas Young's famous double-slit experiment, which showed that light creates interference patterns just like waves on water. Augustin-Jean Fresnel added mathematical descriptions of diffraction, reinforcing the wave model. But the real leap forward came with James Clerk Maxwell in the 1860s. Maxwell unified electricity and magnetism into a single framework and wrote down equations that described how electric and magnetic fields interact. These equations predicted that electromagnetic waves should travel at a fixed speed. When Maxwell plugged in the numbers for the constants of electricity and magnetism, he found the speed of these waves matched the known speed of light. The conclusion was staggering. Light itself was an electromagnetic wave. For the first time, the speed of light was not just an experimental curiosity, it was a fundamental consequence of the laws of physics. Still, mysteries remained. The prevailing belief in the late 19th century was that light waves, like sound waves in air, needed a medium to travel through. Physicists called this medium the luminiferous ether, an invisible substance supposedly filling all of space. If Earth moved through the ether, the speed of light should vary depending on our motion relative to it, just as the speed of sound depends on whether you move with or against the wind. But in 1887, Albert Michelson and Edward Morley performed their famous experiment to detect this ether wind. They used a device called an interferometer to compare the speed of light in different directions as Earth moved around the Sun. To their surprise, they found no difference at all. Light's speed was constant regardless of Earth's motion. The ether, it seemed, did not exist. This paradox, why the speed of light remained constant regardless of motion, set the stage for Einstein. In 1905, Einstein published his theory of special relativity, turning the whole picture upside down. Instead of trying to explain light's constancy by inventing a medium, Einstein boldly declared that the constancy was a fundamental principle of nature. The speed of light, he argued, is the same for all observers, no matter how fast they are moving. To make this work, space and time themselves must be flexible, warping in response to motion. In one stroke, Einstein eliminated the ether, explained the Michelson-Morley results, and placed the speed of light at the very heart of physics. This progression, from immense astronomical observations, through Fizeau and Foucault's experiments, to Maxwell's unification and Einstein's relativity, shows how generations of thinkers chipped away at the mystery of light. Each step was built on the previous, and each revealed a deeper truth. Light was not just a phenomenon to be measured but a key to unlocking the structure of the universe. And this is where our journey naturally flows into the next stage. Because Einstein didn't just clarify the mystery of light, he redefined reality itself. To understand why the speed of light is the ultimate limit, we must look at how Einstein's revolution put this constant at the very center of space, time, and motion. By the time Einstein entered the scene in the early 20th century, the scientific world was standing at a crossroads. The experiments of Michelson and Morley had shaken confidence in the old ether theory, and Maxwell's equations had already suggested that the speed of light wasn't just a property of photons but something woven into the mathematics of electromagnetism itself. What Einstein did in 1905 with his theory of special relativity was nothing short of a conceptual earthquake. He didn't just adjust the numbers to fit the data, he rewrote the rules of reality so that the speed of light was not an afterthought but the very cornerstone of how space and time operate. The brilliance of Einstein's approach was his willingness to take two principles as absolute truths, even if they seemed contradictory to everyday intuition. First, he declared that the laws of physics must look the same for all observers, no matter how fast they're moving in a straight line. This principle of relativity extended Galileo's old idea, that motion is relative to all of physics. Second, Einstein asserted that the speed of light in a vacuum is constant for all observers, regardless of their relative motion. No matter how fast you're moving, if you measure a beam of light, you'll always get the same number, roughly 299,792 kilometers per second. On the surface, these two statements seem impossible to reconcile. If you're running toward a moving object, its speed relative to you should increase. If you're running away, it should decrease. That's how everything else in life works, from baseballs to bullets. But Einstein showed that the universe doesn't work that way for light. Instead, it's space and time themselves that bend to preserve the constancy of light's speed. Lengths contract, time slows down, and simultaneity, the idea that two events happen at the same time, becomes relative. This is where Einstein's revolution truly begins. Before him, space was thought of as a rigid stage on which events played out, and time ticked forward uniformly for everyone everywhere. Einstein demolished this picture. He revealed that space and time are not independent backdrops but interconnected into what we now call space-time. The speed of light, c, is the conversion factor that stitches the fabric of space-time together. It's the ultimate ruler and stopwatch, setting the scale for how distances and durations are measured. Without the constancy of light speed, this unified space-time structure collapses. One of the most astonishing results of Einstein's relativity is time dilation. If you move close to the speed of light, your clock ticks more slowly compared to someone standing still. This isn't an illusion or a trick of perspective. It's a real physical effect confirmed by countless experiments. Muons, subatomic particles created in the upper atmosphere, should decay in microseconds, too quickly to reach Earth's surface. Yet because they travel close to light speed, time for them slows down, allowing many to survive the journey. Similarly, atomic clocks on fast-moving satellites tick differently than those on Earth, a fact that engineers must account for to make GPS technology work accurately. Another equally strange consequence is length contraction. From the perspective of a fast-moving observer, distances in the direction of motion shrink. If you could somehow approach light speed in a spaceship, the entire galaxy in front of you would appear compressed, as though space itself were giving way. These distortions aren't just abstract predictions. They emerge directly from the mathematics of relativity, all to preserve the universality of light's speed. Perhaps the most dramatic outcome of Einstein's theory is the redefinition of simultaneity. In Newton's universe, time was absolute. Events happened at specific moments, universally agreed upon. Einstein showed that simultaneity depends on your frame of reference. Two observers moving relative to each other may disagree about whether two events occurred at the same time, and both would be correct within their own perspective. The one thing they cannot disagree on, however, is the speed of light. That remains fixed for all. In this way, Einstein elevated the speed of light to a position unlike anything else in physics. It became the universal constant, the ceiling of motion, and the keystone of space-time geometry. His famous equation E=mc² emerges from the same framework, showing that mass and energy are two forms of the same thing, linked by the square of light speed. The equation doesn't just describe nuclear power or particle physics. It reveals that C is fundamental to the very relationship between matter and energy. Einstein's revolution also resolved the lingering tension between Maxwell's electromagnetic theory and mechanics. Before relativity, physicists puzzled over how to make sense of Maxwell's equations in moving reference frames. By taking the constancy of light as a postulate, Einstein showed that the laws of electromagnetism and mechanics could coexist harmoniously within the same framework, but only if we abandoned the idea of absolute time and space. It's difficult to overstate the impact of this conceptual leap. With special relativity, Einstein didn't just solve a scientific puzzle, he redefined our understanding of reality. The speed of light was no longer just a number describing how fast illumination spreads. It became the cosmic speed limit, the hinge upon which the doors of space and time swing. Everything that moves, from particles and accelerators to galaxies racing apart in the expanding universe, must conform to this limit. And this leads naturally into the next part of our exploration. If Einstein's theory placed the speed of light at the center of space-time, then we must understand what that really means for how space and time themselves behave. Because relativity tells us something profound, these aren't fixed, absolute entities, but elastic dimensions that depend on how fast you move. When Einstein put the speed of light at the heart of physics, he shattered an idea that had guided human thought for centuries, that time and space were absolute. Before relativity, people thought of time as a universal clock ticking away in the background, the same for everyone, everywhere, regardless of what they were doing. Likewise, space was imagined as a rigid, unchanging stage where the drama of the universe unfolded. Events occurred at fixed places and fixed times, and everyone, in principle, could agree on them. It was comforting, intuitive, and deeply wrong. Einstein showed that time and space are not absolutes, they are relative, and their behavior depends on your motion. This was the radical heart of special relativity. The very measurements we take for granted, how long something lasts, how far apart 2 points are, or whether 2 events happen at the same moment, change depending on how you're moving. That sounds bizarre, even impossible, until you realize it's the only way the universe can preserve the constancy of light's speed. Let's start with time. In relativity, time is not a universal river flowing the same way for everyone. Instead, it's like a personal stream attached to each observer. The faster you move relative to someone else, the slower your clock ticks compared to theirs. This effect is called time dilation. Imagine you're an astronaut traveling near the speed of light. For you, time feels completely normal. You eat, sleep, and age at your usual pace. But when you return to Earth, you might discover that decades have passed for everyone else while only a few years passed for you. It's not science fiction. It's a direct consequence of how the universe works. This isn't just theory. It's been tested. One of the most striking confirmations comes from experiments with subatomic particles called muons. These particles are created when cosmic rays strike Earth's atmosphere. At rest, muons decay in about 2 millionths of a second, far too short a time to travel from the upper atmosphere to the surface. Yet we detect huge numbers of muons at ground level. The reason? They are traveling so close to the speed of light that their internal clocks slow down relative to Earth, allowing them to survive the journey. Particle accelerators replicate this every day, with unstable particles living longer than they would if at rest, all thanks to relativity. Now consider space. Just as time dilates, space contracts. If you're moving near the speed of light, distances in the direction of your travel shrink. This is called length contraction. Suppose your spaceship is headed toward a distant star 10 light-years away. From Earth's perspective, it would take at least 10 years for light to get there, so no spaceship could possibly make it faster. But for you on board, space itself compresses along your path. The distance to the star shrinks, meaning you can reach it in much less of your own personal time, even though Earth observers still see your speed capped by light. Both views are correct, because space and time adjust differently for each observer. What relativity teaches us is that space and time are not independent, fixed quantities. They are part of a single fabric, space-time, that flexes and reshapes itself depending on motion. The constant speed of light is the thread that binds this fabric together. When you move faster, you borrow from one dimension to pay the other. Speeding up makes your time slow down and your distances shrink, but always in just the right way so that no matter what, light still races past you at the same unchanging speed. This relativity of time and space also destroys the old idea of simultaneity. Imagine 2 lightning bolts striking opposite ends of a moving train at the exact same moment from the perspective of someone standing on the ground. For the passenger inside the train, however, the flashes will not appear simultaneous. If the train is moving forward, the passenger is rushing toward the light from the front strike and away from the light from the rear strike. Because light speed is constant, the light from the front will reach them later, and the light from the back sooner. To the passenger, one bolt happened before the other. Who is right? Both are. Simultaneity is relative. It depends on your frame of reference. This realization, that even the order of events can depend on motion, was shocking when Einstein first proposed it. But it is the logical outcome of tying time and space to the universal speed limit of light. In Newton's universe, events unfolded on a stage that everyone could agree upon. In Einstein's universe, each observer carries their own coordinate system of space and time, stitched together by the constancy of c. The implications reach far beyond thought experiments. Relativity governs real-world technologies. Global Positioning System, GPS. Satellites orbit Earth at high speeds and experience weaker gravity than we do on the surface. Both special relativity, because of their speed, and general relativity, because of their altitude in Earth's gravity well, affect their onboard clocks, making them tick at different rates than clocks on Earth. Without correcting for these effects, GPS would drift by kilometers every day. In other words, the phone in your pocket works because engineers accounted for the relativity of time and space. When you grasp this, you begin to see that the speed of light is more than just a maximum velocity. It is the mechanism that forces space and time to behave flexibly. It's what ensures the laws of physics remain consistent for everyone, no matter their motion. Instead of treating time as a single cosmic rhythm and space as a rigid grid, we now understand them as interdependent dimensions, always relative, always shaped by the motion of observers. And this realization leads us naturally into the next step of the story. If time and space themselves bend and stretch around the speed of light, then the role of light becomes even greater than we might think. It's not just about photons streaking across the void, it's about how the very fabric of space-time is built. Once we begin to see that time and space are not rigid absolutes but pliable dimensions shaped by motion, the role of light itself takes on a much deeper meaning. At first glance, the phrase "the speed of light" makes it sound as though we're just talking about how quickly photons move. But Einstein's revolution revealed that light isn't the main character in this story, it's the messenger. What we call the speed of light is actually something more profound, the universal conversion factor, the cosmic boundary woven into the very structure of space-time. To understand this, think about what it means to measure space and time. We measure distance in meters, and we measure time in seconds. At first, these might seem like separate, unrelated units. But relativity shows that they're actually two sides of the same coin. The constant c, the speed of light, is the bridge that connects them. When physicists write equations, they often even set c equals 1, not because light is trivial, but because it shows that distances in space and durations in time can be transformed into one another. It's like realizing that centimeters and inches are just different expressions of length. Space and time are different expressions of space-time, with c as the translator. This means that the value of c is not just the speed of photons darting around the cosmos. It's the maximum rate at which cause and effect can be linked. It's the ultimate communication channel for the universe. Any particle, any signal, any ripple in space-time itself must respect this limit. Light just happens to be our most familiar example because photons are massless and therefore always travel at this speed. But in truth, if photons didn't exist, if light as we know it weren't around, the constant c would still appear in the mathematics of space-time. It would still set the maximum rate of information transfer. It would still be the foundation upon which relativity rests. Think about how space-time diagrams are drawn in relativity. Imagine plotting time on the vertical axis and space on the horizontal axis. In such a diagram, the path of a light beam always traces out a line at exactly 45 degrees. No matter what observer you choose, those lines of light remain the same. These lines mark the limits of what can influence what. Anything inside the light cone of an event can be causally connected to it. Anything outside is forever unreachable. This isn't a property of light as such, it's a property of space-time. Light simply shows us the geometry in action. The universality of this constant is also why relativity reshapes how we think about motion. Normally, when you add speeds, they stack up. If you're in a car moving at 100 km per hour and you throw a ball forward at 20 km per hour, the ball is going 120 km per hour relative to the ground. But if you shine a flashlight out the window of that car, the light doesn't add to your speed. It doesn't go faster than c just because you're moving. It still moves at c relative to you, and also at c relative to the ground, and also at c relative to anyone else. The only way this works is if space and time themselves flex, adjusting distances and durations for each observer, so that the speed of light never changes. This constancy has another consequence. It sets the scale for relativity's most famous equation, E equals mc squared. Notice that the speed of light here doesn't mean the motion of photons. It means the universal conversion rate between mass and energy. The square of c tells us how much energy is stored in a given mass. It's enormous because c is enormous. A single gram of matter contains about as much energy as the explosion of a small nuclear weapon. This equation works not because light is special as a substance, but because c is embedded in space-time itself, governing the relationship between matter and energy. It's worth emphasizing how strange this is. In most sciences, constants are properties of things. The melting point of water is a property of water. The gravitational pull of Earth is a property of Earth. But the speed of light is not a property of photons, it's a property of reality. It defines the stage on which all physical processes play out. When we say nothing can go faster than light, we're not really saying nothing can catch up to photons. We're saying nothing can exceed the maximum speed built into spacetime itself. Even in phenomena beyond light, this role is evident. Gravitational waves, the ripples in spacetime predicted by Einstein and confirmed a century later by LIGO, also travel at exactly the speed of light. Why? Because they too are not bound to some medium. They are disturbances in the very geometry of spacetime, and thus they propagate at the universal constant of causality. So when we talk about the speed of light, we're really using a familiar name for something much deeper: the absolute limit of the universe, the defining constant of spacetime. Photons simply happen to surf along this boundary because they lack mass. Everything else, no matter how much energy we pump into it, can only asymptotically approach this limit. And this is where the next piece of the puzzle becomes clear. If C is the bedrock of spacetime, then its relationship to matter and energy is just as fundamental. Einstein gave us not just relativity but also the famous link between mass and energy. To truly understand why light speed is a limit, we have to see how matter itself is tied to energy through this constant. When Einstein revealed that the speed of light wasn't just a number but a cosmic constant tied to the structure of spacetime, he also uncovered one of the most famous and transformative equations in history: E=mc². At first glance, this little formula looks almost too simple. It's just 3 letters and a square. But hidden inside it is a revelation that completely redefined how we understand matter, energy, and the universe itself. It says that mass and energy are not separate substances, as people once believed. They are interchangeable, 2 faces of the same underlying reality, connected by the square of the speed of light. Let's unpack this carefully. E stands for energy, m stands for mass, and c² is the square of the speed of light. The equation states that the energy contained in any object at rest is equal to its mass multiplied by the square of c. Because c is such a huge number, about 300,000 kilometers per second, the value of c² is almost unimaginably large. That means even a tiny amount of mass contains a staggering amount of energy. To put it in perspective, 1 kilogram of matter, if fully converted into energy, would release about 90 trillion joules of energy. That's enough to power an entire country for days, or to create an explosion far greater than any conventional bomb. In fact, this principle is what underlies both nuclear power and nuclear weapons. When atomic nuclei fuse together, as in the Sun, or split apart, as in a nuclear reactor, a small fraction of their mass is converted into energy. That small fraction, multiplied by c², produces enormous energy yields. But E=mc² is not just about bombs or stars. It reveals something far more profound. Mass itself is a kind of frozen energy. What we perceive as the solid, heavy matter around us is, in a sense, concentrated energy locked into form. Conversely, energy itself can produce mass. High-energy collisions, such as those in particle accelerators, can create entirely new particles. Photons, the quanta of light, have no rest mass, but when 2 collide with enough energy, they can produce matter-antimatter pairs, literally creating mass from pure energy. This symmetry shows that mass and energy are not 2 separate things but interchangeable states of a single substance. This realization also reshaped how we think about the cosmos. In the heart of stars, hydrogen atoms fuse into helium, converting a tiny portion of their mass into light and heat that radiates outward. That's why the sun shines and why life on Earth is possible. Without E=mc², the processes powering stars and creating the heavy elements necessary for planets and biology would not make sense. The very atoms in our bodies were forged in stellar furnaces, where mass became energy, and energy forged new matter. The equation also explains why the speed of light appears squared. It's not arbitrary, it reflects the depth of the link between mass and energy. To convert mass to energy, you scale it by the square of the universal constant that ties together space and time. That square gives the conversion its vast multiplier, making even small bits of mass enormously energetic. It's as though the fabric of space-time itself dictates the exchange rate between matter and energy, and that exchange rate is determined by c². The beauty of Einstein's insight is that it unifies what once seemed totally different. Before relativity, physicists treated energy and mass as distinct quantities. Mass was the stuff that made up objects, energy was what made them move or change. Einstein showed they were two aspects of the same coin. This unification is a hallmark of physics. When we find deeper truths, we often discover that seemingly separate concepts are actually one. Electricity and magnetism were unified by Maxwell. Space and time were unified by Einstein. Now mass and energy joined the same path. There are also subtler consequences. In relativity, the mass of an object is not just a passive measure of how much matter it contains, it's also a reservoir of potential energy. That's why particles and accelerators become harder and harder to accelerate as they approach light speed. Their kinetic energy contributes to their effective mass, tying back to E=mc². It's not simply that mass turns into energy or vice versa. It's that they are always interwoven, shifting forms depending on context. What's remarkable is how this principle shows up in our daily lives, even if we don't notice it. Every breath you take contains oxygen atoms formed in long-dead stars. The energy your body uses to move and think ultimately comes from the sun, where nuclear fusion has been transforming mass into energy for billions of years. The heat in your coffee cup, the electricity in your phone, the chemical energy in food, all of it is part of this great interchange, governed by Einstein's simple yet profound equation. And this realization naturally sets the stage for the next step in our journey. If mass and energy are two forms of the same thing, then trying to push an object with mass to the speed of light runs into an extraordinary problem. The energy required doesn't just increase steadily, it skyrockets. The closer you get to the speed of light, the more energy you need, until it approaches infinity. Understanding this infinite energy barrier is key to understanding why light speed isn't just a practical limit but an unbreakable law of physics. When Einstein revealed that mass and energy are two forms of the same reality, a profound consequence followed: the way objects behave as they accelerate. At everyday speeds, cars on a highway, airplanes in the sky, even rockets orbiting Earth, the relationship between speed and energy feels straightforward. The faster you go, the more energy you need, but it scales in a way that seems manageable. Push harder, burn more fuel, and you go faster. That's the intuition we grow up with, the Newtonian picture. But once you push into the realm of relativity, once you start nudging closer and closer to light speed, the story changes completely. The energy demands explode in a way that makes the speed of light an unreachable wall for anything with mass. To see why, let's look at how kinetic energy behaves in relativity. In classical mechanics, the kinetic energy of an object is given by a simple formula: 1/2 times mass times velocity squared. Double the velocity, and the kinetic energy goes up 4 times. But this formula breaks down at high speeds. Einstein's relativity gives us a different picture. The total energy of an object is tied to its mass through the famous equation E=mc², but that's only the rest energy. When you add motion, the equation becomes more complex. The energy depends not just on the object's mass but on how close its velocity is to the universal constant, c. As an object accelerates, its momentum and energy increase in a way described by the Lorentz factor, a mathematical term that grows without bound as velocity approaches the speed of light. The Lorentz factor is written as 1 divided by the square root of 1 minus v squared c squared. At low speeds, this factor is close to 1, so relativity barely affects things. But as v, the object's velocity, approaches c, the denominator shrinks towards 0. The result is that the factor, and thus the energy needed to keep pushing the object, increases toward infinity. No matter how much energy you supply, you can never quite push a massive object to match the speed of light. You can get closer and closer, but the required energy shoots upwards so steeply that the final step would require infinite energy, which is impossible. This isn't just an abstract calculation. Particle accelerators like the Large Hadron Collider in Switzerland live this reality every day. Protons are whipped around a 27-kilometer ring at speeds reaching 99.9999991% of the speed of light. At those speeds, The protons carry thousands of times more energy than their rest mass alone. But despite all the colossal machinery and staggering amounts of energy poured into them, the protons never actually reach light speed. They asymptotically approach it, getting unimaginably close, but the wall of infinite energy keeps them just shy of the barrier. Think about what this means in practice. Suppose you're a spaceship pilot with the most powerful engine imaginable. At first, your acceleration feels smooth, you're burning fuel, gaining speed. But as you push harder, the returns diminish. For every extra fraction of a percent closer to light speed, you must pump in vastly more energy than before. Eventually, the energy cost becomes absurd. To reach 99% of light speed already takes an enormous amount. To reach 99.9% takes far more. By the time you aim for 99.999%, the energy requirement is so colossal it outstrips the output of entire stars. And yet, even then, you wouldn't actually hit the light speed limit. You'd just crawl ever closer, like a swimmer trying to catch the horizon. This infinite energy barrier is not just a practical obstacle, it's a law of nature. It's the universe's way of saying, this boundary cannot be crossed. Just as the square root of a negative number is undefined in the realm of real numbers, trying to accelerate a massive object to the speed of light breaks the rules of spacetime itself. The math doesn't allow it. Interestingly, this principle also ties back to the conservation of energy and causality. If it were possible to accelerate matter to or beyond light speed, it would throw the entire bookkeeping of the universe into chaos. The balance between mass and energy would collapse, signals could overtake their causes, and relativity's careful structure would unravel. The infinite energy requirement is, in a way, a safeguard. It ensures the universe stays consistent. We can see a smaller scale version of this when thinking about why rockets can't simply push harder forever. Rockets work by expelling fuel mass at high velocity. To go faster, you must carry more fuel. But the more fuel you carry, the heavier your rocket becomes. The heavier it is, the more fuel you need to accelerate that fuel. This feedback loop already makes space travel fiendishly difficult at ordinary speeds. Now multiply that challenge by the relativistic wall, and you see why just add more thrust doesn't get you anywhere near light speed. The energy problem isn't one of engineering. It's built into the mathematics of reality. This infinite climb in energy requirement is what separates photons, which have no rest mass, from every other particle in the universe. Photons don't need energy to reach light speed, they are born there. But for us, for matter, the energy cost ensures we remain forever below that ultimate limit. And this is the natural bridge to the next realization. If the energy keeps increasing without bound as you approach light speed, then it's not just the fuel problem that grows, it's the mass itself. The very inertia of the object, its resistance to acceleration, increases. To see why acceleration gets harder and harder, we must talk about how mass itself changes as you speed up. The story of why nothing can reach or exceed the speed of light becomes even more vivid when we examine how mass behaves at high velocities. In everyday life, mass seems like a fixed property. A bowling ball weighs the same whether it sits on your porch or rolls down the alley. But relativity tells a different story. As an object moves faster, its effective mass, sometimes called relativistic mass, increases, making it progressively harder to accelerate. This isn't just a mathematical curiosity. It's a fundamental feature of how the universe prevents anything with mass from ever catching up to light. The idea is closely tied to what we just discussed about energy. Recall that the energy required to accelerate an object grows dramatically as you approach the speed of light. This is because, in relativistic terms, energy and mass are intertwined through Einstein's equation, E equals mc squared. As you pump energy into a moving object, some of that energy doesn't just increase its speed, it increases its relativistic mass, making it effectively heavier. In other words, the faster you go, the more stuff there is to push, and the harder it becomes to accelerate further. Mathematically, the relativistic mass m, v, is expressed as the rest mass m multiplied by the Lorentz factor. m, v, equals m square root, 1, v squared c squared. At low velocities, v is tiny compared to c, so the Lorentz factor is almost 1, and relativistic mass is nearly the same as rest mass. That's why everyday motion feels normal and Newtonian physics works so well at speeds we experience. But as v approaches c, the denominator approaches zero, causing m.v. to soar toward infinity. This means that an object moving close to light speed behaves as though it has become infinitely massive. No amount of applied force can push it to or past the speed of light. This concept explains why particle accelerators, which we briefly touched on earlier, require exponentially more energy as particles near light speed. Protons at the Large Hadron Collider, for example, reach 99.9999991% of the speed of light, but the energy required to get the last fractions of a percent is astronomical. The particles become so heavy in a relativistic sense that further acceleration demands resources far beyond what is feasible. This is not a limitation of technology, it is a reflection of the intrinsic rules of the cosmos. The increase in effective mass also has practical consequences in physics experiments and space travel. Engineers designing high-speed vehicles or particles must account for relativistic effects. Ignoring them would lead to gross errors in timing, energy requirements, and momentum calculations. Even in everyday technology, relativistic mass effects appear indirectly. GPS satellites, moving at high speed relative to Earth's surface, experience time differently, and these tiny discrepancies must be corrected for the system to remain accurate. Relativistic mass also explains why photons are so unique. Since they have no rest mass, the Lorentz factor doesn't apply, they don't gain mass as they travel. This is why light can coast at sea freely, unimpeded by the infinite energy barrier that applies to matter. Photons always travel at light speed because, from the universe's point of view, they are massless travelers riding exactly along the fabric of spacetime's natural limit. The concept also deepens our understanding of why acceleration behaves asymptotically near light speed. Think of pushing a massive truck. At first, you apply force and the truck moves. Push harder, and it moves faster. But imagine a truck whose mass grows with speed. Every increase in velocity makes it heavier, demanding even more force to gain additional speed. Near the light speed limit, the truck is effectively infinitely heavy, and no finite force can push it faster. This is exactly the behavior of matter in relativistic physics. It's fascinating to consider how this reshapes our intuitions about motion. In a Newtonian world, we might dream of infinite acceleration. Just keep pushing, and you could reach any speed. But in the relativistic universe, the cosmos imposes a built-in speed governor. It's not imposed arbitrarily. It emerges naturally from the interplay between energy, mass, and the geometry of space-time. The faster you go, the more resistant you become to going faster still. The energy wall and the mass increase are two sides of the same coin, both consequences of the same underlying principle. The structure of space-time itself enforces the ultimate speed limit. This understanding leads us seamlessly to another key insight. If matter's mass increases with speed, it explains why photons, which have no rest mass, are fundamentally different. They are not bound by this relativistic mass effect, and as a result, they always move at c. Studying photons illuminates the boundary between what can be accelerated and what is forever fixed at light speed, highlighting the stark divide between massless and massive entities in the universe. And naturally, once we grasp this, the next question emerges. What exactly happens at the speed of light itself? If we try to imagine a massless particle traveling at c, or matter attempting to reach that speed, strange and extreme phenomena occur. Time and space behave in ways that defy ordinary intuition. That is the next stage of our exploration. Photons occupy a unique and extraordinary place in the universe. Unlike electrons, protons, or even entire spacecraft, photons have no rest mass. This absence of mass is what allows them to move at the cosmic speed limit, the speed of light, c, without restriction. While everything with mass faces an infinite energy barrier as it approaches light speed, photons are born to travel at exactly this velocity, a property that fundamentally distinguishes them from the rest of the material universe. Rest mass is, in essence, the weight of existence an object carries even when it's at rest. A proton, for instance, weighs roughly 1.67 times 10 to the power of negative 27 kilograms, and an electron about 9.11 times 10 to the power of negative 31 kilograms. This mass determines how much energy is required to accelerate the particle. As we discussed in the previous segment, the closer a massive object gets to light speed, the more its effective mass increases, making further acceleration progressively harder. But photons start their existence differently. They have zero rest mass. That means they don't encounter this relativistic mass problem. They don't need to be accelerated to light speed, they simply always travel there. This massless nature of photons explains why light behaves so differently from matter. For massive particles, velocity and momentum are linked through their mass. To gain more momentum, you must increase energy, and as velocity approaches c, the energy required climbs toward infinity. Photons, however, derive their momentum entirely from their energy, which is tied to their frequency or wavelength via Planck's relation. E equals hf, where h is Planck's constant and f is frequency. Because photons have energy without rest mass, they automatically satisfy the condition for moving at c. Their momentum exists independently of rest mass, and so they glide effortlessly at the universal speed limit. Photons also exhibit another remarkable property: they are always in motion. Unlike massive objects that can sit still, photons cannot exist at rest. They are intrinsically dynamic, always traveling, because their energy is inseparable from their motion. Attempting to stop a photon would require removing all of its energy, effectively annihilating it. In a sense, photons are defined by their motion. They are the ultimate travelers of space-time. This special status also underpins why light plays such a critical role in relativity. Photons define the structure of light cones, the boundaries of causality in space-time. Their paths demarcate what events can influence each other. Because they always move at c, they trace out the maximum speed at which any signal or interaction can travel. Any faster motion would require violating the space-time fabric itself, something that is fundamentally forbidden. In this way, photons are not just passive particles, they are indicators of the universe's ultimate speed limit. The massless nature of photons also explains why the universe is capable of transmitting information across vast distances. Light from the sun reaches Earth in about 8 minutes, giving us information about the sun's state in near real time. Similarly, electromagnetic signals carry data across the cosmos, from radio waves sent to distant spacecraft to X-rays emitted by exploding stars, all traveling at c. If photons had mass, these signals would slow down as they moved, making the universe far less coherent and predictable. Photons' special status also influences the structure of energy in the cosmos. Because they are massless, they contribute to radiation pressure, drive solar sails, and interact with matter in ways that massive particles cannot. In the early universe, photons dominated energy density, shaping cosmic evolution before matter took precedence. Their constant speed allowed them to propagate uniformly, smoothing out temperature variations and influencing the formation of galaxies and cosmic structures. It is important to note, however, that being massless does not make photons exempt from the influence of gravity. Through Einstein's general relativity, we know that spacetime curvature affects all particles, massless or massive. Light bends around massive objects, a phenomenon observed as gravitational lensing. Even though photons have no rest mass, their energy and momentum interact with spacetime, making them subject to the warping of gravity, but never altering their intrinsic speed of c. Photons also demonstrate the principle that the speed of light is more than just about light itself. They are the universe's messengers, but the speed they move at is a reflection of spacetime structure. If photons didn't exist, the constant c would still dictate the maximum speed of information, the geometry of spacetime, and the causal order of events. In essence, photons serve as both participants in and indicators of the universal speed limit. All these factors converge to make photons unique, always massless, always moving, always traveling at c, and always defining the ultimate boundary for speed, information, and causality in the universe. Their nature demonstrates why light speed is not an arbitrary number but a foundational property of reality. Understanding photons sets the stage for considering what happens if an object were to hypothetically reach light speed itself. What would happen to time, space, and observation at this ultimate frontier? Exploring that question leads us to the mind-bending effects of traveling at light speed, where time dilation becomes infinite, and distances along the direction of travel shrink to zero. Once we truly grasp why photons are special, it naturally leads us to ask, what happens at light speed itself? What would it be like to travel at c? Here, physics departs entirely from our everyday intuition and enters a realm where space and time behave in ways that seem almost paradoxical. While no object with mass can reach light speed, Imagining what happens at that limit highlights the extreme consequences of relativity and why the cosmic speed limit is so absolute. One of the most striking effects is time dilation. As we saw earlier, time slows down for objects moving close to the speed of light relative to a stationary observer. The faster you go, the more pronounced this effect becomes. Mathematically, time dilation is governed by the Lorentz factor, gamma equals 1 square root 1 v squared c squared. As velocity v approaches c, the denominator approaches 0, causing gamma to approach infinity. In physical terms, this means that time, from the perspective of a stationary observer, effectively stops for an object moving at light speed. Consider a thought experiment. Imagine a photon traveling from the Sun to Earth, a distance of about 150 million kilometers. From our perspective, it takes approximately 8 minutes for light to cover that distance. But from the photon's perspective, if such a perspective could exist, time does not pass. Those 8 minutes are instantaneous. For the photon, the departure and arrival happen simultaneously. This is not science fiction. It's a direct consequence of the relativistic equations governing time and space. Time dilation becomes infinite at light speed, illustrating why massive objects can never achieve this velocity. Their clocks would have to stop completely, a physical impossibility for matter with mass. Equally mind-bending is length contraction, which occurs along the direction of motion. As an object approaches light speed, distances in the direction it travels shrink according to the same Lorentz factor. For velocities extremely close to c, this contraction becomes extreme, approaching 0. If a photon could measure the distance between the Sun and Earth along its path, it would perceive the two as coinciding, essentially no distance at all. The entire universe along the direction of travel is compressed into a point. This explains why light can cross astronomical distances without experiencing them in the same way that massive objects do. Space itself is effectively flattened along the motion of a massless particle. When we combine these two effects, time dilation and length contraction, the picture becomes even more extraordinary. At light speed, time stops, and distance in the direction of travel vanishes. In a sense, the photon experiences an instantaneous journey across the cosmos. This also highlights why no massive object can reach light speed. If time were to stop for that object, it could not perform any physical processes. Chemical reactions, structural integrity, or information transfer would all cease. The laws of physics simply do not allow matter to exist at that boundary. It's also worth noting that at light speed, the concept of simultaneity collapses entirely. Events that are separate in space and time from a stationary observer's viewpoint collapse into a single, instantaneous occurrence from the perspective of a photon. Cause and effect, as we understand them for massive objects, lose their usual meaning. This underlines the unique role photons play in the universe. They travel at c, but they do not experience time or distance in the conventional sense. Their journey is fundamentally different from anything with mass. The relativistic effects at light speed also underscore why massless particles are immune to the energy barriers that prevent massive objects from reaching c. For a massive particle, approaching light speed, relativistic mass. For a photon, these constraints do not apply. Its energy is entirely in motion, and no mass exists to resist acceleration. That is why light naturally moves at c from the instant of its creation. These extreme effects, time stopping, distance vanishing, simultaneity collapsing, also clarify a subtle but crucial point. Imagining riding a photon is physically meaningless. We cannot inhabit the reference frame of light, because the frame itself would require time to stop completely and distances to shrink to 0. Any attempt to conceptualize light's perspective is doomed by the laws of physics demands infinite energy and leads to infinite themselves. This is not a limitation of our imagination. It is a fundamental property of space-time and relativity. Moreover, these phenomena have profound implications for the transfer of information. Since massive objects can never reach light speed, signals, matter, or energy are all constrained to move at or below c. Faster than light travel or communication would violate causality because, at c, the usual ordering of cause and effect breaks down. Events that occur in sequence for one observer could appear reversed for another, opening the door to paradoxes. The infinite dilation of time and the zero distance along the direction of travel are what enforce this ultimate speed limit in a consistent way. This leads naturally into the next insight: no observer can ride light. Photons are the ultimate carriers of c, but trying to imagine yourself moving at that speed doesn't make sense physically. Any object with mass cannot experience light speed travel because it would require stopping time entirely and collapsing the space in front of it. These constraints show that the speed of light is woven into the fabric of reality itself. It is not just a number, but a limit embedded into the structure of space-time. Once we understand what happens at light speed, the infinite time dilation, the zero-length contraction, the collapse of simultaneity, it becomes clear why imagining yourself riding alongside a photon is physically meaningless. In everyday life, we can switch perspectives, place ourselves in a moving car, and describe motion relative to that frame. But photons are in a fundamentally different category. Their motion at c lies outside the realm of any possible reference frame for an object with mass, and trying to adopt such a frame is not merely difficult, it is impossible according to the laws of physics. The first reason is rooted in time dilation. For an object moving at light speed, time effectively stops. All processes freeze. For a photon, there is no internal clock ticking forward. No chemical reactions, no internal vibrations, no passage of experience. Nothing occurs in the usual sense. If you tried to ride alongside a photon, your own biological processes, thoughts, and measurements would all have to stop completely to match the photon's frame. That is physically absurd. Our existence, like all matter, depends on the flow of time. Without it, nothing can happen. The very concept of experience or observation disappears. Second, the geometry of space itself forbids a reference frame at light speed. Length contraction along the direction of motion shrinks distances to zero. If you could somehow occupy a light speed frame, the universe in front of you would collapse into a single point. The space you would perceive is literally non-existent, so there is nowhere to move through and nothing to observe. Space and time are intertwined in a way that only allows a meaningful frame for subliminal, slower than light, motion. Massless particles, like photons, exist in the light speed domain, but they don't inhabit it in the sense of experiencing a perspective. There is simply no coherent way for a material observer to attach themselves to that frame. Another subtle reason involves energy and mass. As discussed previously, the closer an object with mass approaches c, the more its relativistic mass grows, and the energy required for further acceleration skyrockets. To match light speed, the required energy becomes infinite. This isn't just a technological limitation, it's a physical impossibility. You cannot create infinite energy, nor can matter exist in a state where it has infinite inertia. Thus, attempting to ride light would require violating fundamental conservation laws and relativity itself. The universe enforces the speed limit through this insurmountable barrier. Furthermore, the notion of riding light would disrupt causality. In relativity, the sequence of cause and effect is maintained by the limit set by c. Events cannot influence other events faster than light, or the order of cause and effect could reverse in some frames, creating paradoxes. If a human observer could move at c, they could, in principle, see effects occur before causes, a logical contradiction. The impossibility of such a frame preserves the consistency of physical law. In other words, the universe forbids light-speed reference frames for massive observers to prevent logical breakdowns in causality. This explains why, despite endless popular depictions in science fiction of riding a beam of light, or traveling alongside photons, such scenarios are fundamentally flawed. Photons don't experience motion, they are not sentient, and they don't carry clocks or rulers. Light-speed travel is not just extremely fast, it is an entirely different category of existence, one that matter cannot enter. Any attempt to adopt a photon's perspective violates the very structure of spacetime. Interestingly, this also emphasizes how unique photons are. They inhabit a domain where motion at c is natural and necessary, but they do not experience that motion as a reference frame. In contrast, every particle with rest mass experiences time, has length, and can occupy a frame of reference, but these features prevent it from reaching c. The two worlds, massive matter and massless light, are complementary yet strictly separated by the laws of physics. This naturally leads to the next consideration: why the speed limit matters not just for particles, but for the flow of information. Because no observer can ride light and massive objects cannot exceed c, faster-than-light signals are impossible, ensuring that cause and effect remain consistent across the universe. This is why the speed of light is more than a number. It is the ultimate boundary for information transfer, communication, and the unfolding of events in space-time. Once we understand that no observer can ride light and that massive objects cannot reach c, the deeper significance of the speed limit becomes clear. It preserves causality, the fundamental ordering of cause and effect. In the everyday world, we take causality for granted. If you flip a switch, the light turns on. If you drop a ball, it falls. Causes precede effects, and this ordering is consistent for all observers moving at subliminal speeds. But relativity shows that if faster-than-light travel or communication were possible, this sacred order could be disrupted, leading to paradoxes that defy logic and the structure of reality itself. Consider a simple thought experiment. Imagine a signal traveling faster than light from point A to point B. In our frame, A sends the signal, and B receives it later. Straightforward enough. But in relativity, observers moving relative to A and B experience time differently due to time dilation and the relativity of simultaneity. For a sufficiently fast-moving observer, the order of events can appear reversed. B could receive the signal before A sends it. Suddenly, the effect precedes the cause. This is not just counterintuitive, it is fundamentally inconsistent. Logic, physics, and the chain of events that define reality would break down. This is why the speed of light is not merely a speed limit for particles but a limit for information transfer. Anything carrying a signal, electromagnetic waves, particles, gravitational interactions, must obey this limit. Allowing faster-than-light communication would mean that information could propagate backward in time relative to some observers, creating paradoxes like the grandfather paradox, where actions could prevent their own cause. Physics, in this sense, enforces C as a universal rule to maintain the logical consistency of the universe. It's worth noting that this limitation applies not just to humans or spacecraft but to all processes, including natural phenomena. Even the propagation of forces is bound by this limit. Gravity, electromagnetism, and nuclear forces all transmit their influence at or below C, ensuring that no interaction violates the order of cause and effect. General relativity confirms this. Gravitational waves propagate at the speed of light, and changes in gravitational fields cannot be communicated faster than c, preserving the causal structure of space-time. From a technological standpoint, this universal speed limit explains why science fiction concepts like instantaneous teleportation or interstellar messaging face insurmountable physical hurdles. Even if we could manipulate space in exotic ways, any signal or influence that would allow information to reach a destination faster than light would create inconsistencies with causality. The universe's rules simply do not allow such violations. This causality constraint also illustrates why tachyons, hypothetical faster-than-light particles, remain purely speculative. While equations may allow for solutions that move faster than light, they come with unavoidable consequences for time ordering. A tachyon signal sent from A to B could arrive before it was emitted in some reference frames, creating paradoxical loops where cause and effect are scrambled. This is more than a theoretical curiosity. It demonstrates why C is deeply tied to the very logic of the universe. The impossibility of faster-than-light information transfer reinforces the universality of light's speed. It's not simply a matter of photons moving fast. C defines the fastest rate at which any influence, energy, or information can travel. It's a cosmic bookkeeping mechanism, keeping all events in a consistent temporal order across all frames of reference. Without it, the universe would lack a coherent causal structure, and predictions, physics laws, and reality itself would unravel. In essence, the speed of light is both a physical and logical limit. It is the ultimate speed not because of technological constraints, rocket engines, or fuel, but because exceeding it would undermine the foundation of time itself. Cause and effect are inseparable from the structure of space-time, and C is the boundary that ensures this structure remains intact. This understanding naturally leads to the deeper question. Why, exactly, is C the universal speed limit? Why does the fabric of space-time enforce this maximum? To answer that, we need to look beyond light itself and see how C governs the ultimate transmission of information and interaction throughout the cosmos. The speed of light, c, is often thought of as simply how fast photons move. But in reality, its significance goes far deeper. C is the universal speed limit because it represents the fastest possible rate at which information, energy, or any causal influence can propagate through the universe. This distinction is crucial. Light is just one manifestation of the fundamental limit, but the limit itself is baked into the geometry of space-time. It governs the rules of causality, the flow of events, and the structure of physical law. At its core, c is the boundary that separates what is possible from what is impossible in terms of communication and motion. Nothing can carry information faster than c. When we say that no object can exceed light speed, we are really saying that no signal can be transmitted faster than c. A signal could be a photon, an electron, a gravitational wave, or any other form of physical interaction. This is why the constancy of c is central to both special relativity and our understanding of the universe. It's not about light per se, it's about the maximum rate at which the universe allows cause and effect to operate. Imagine the universe as a vast network of events, each linked causally to others. Information can only travel from one event to another along paths constrained by c. In spacetime diagrams, these paths are represented by light cones, which define the set of all points that can be causally connected to a given event. Anything inside the light cone can be influenced or influence the event. Anything outside the cone is unreachable. No matter how exotic your technology or how advanced your physics, no influence can jump outside this light cone without violating the fundamental causal structure of spacetime. This framework explains why c appears in so many equations beyond electromagnetism. In relativity, c acts as a conversion factor between space and time. It tells us how to translate temporal intervals into spatial distances and vice versa. In other words, c is a structural feature of spacetime, not merely a property of photons. Its value determines the geometry of the universe, constraining how distances, durations, and interactions are related. Without this limit, the relationships between space, time, and energy would collapse, and the coherent structure of physical law would be lost. Moreover, the universality of c ensures that all observers, no matter their relative motion, agree on the maximum speed of information transfer. This is fundamental for physics to make sense. If different observers measured different ultimate speeds, the ordering of cause and effect could differ between frames, producing paradoxes. The constancy of c preserves a universal causal order, making it possible to predict outcomes, perform experiments, and understand interactions consistently across the cosmos. Another important aspect is that c is independent of the medium or the type of interaction. Light travels at c in a vacuum, but it slows down in water or glass. Yet the ultimate limit remains c, not the speed of light in any medium. This distinction reinforces that the speed limit is about the maximum rate of information transfer in empty space, not about the behavior of a particular particle in a material substance. Even gravitational waves and other massless particles propagate at c, confirming that this limit is universal and not specific to light alone. Understanding c as the universal speed limit also clarifies why science fiction concepts like faster-than-light travel, warp drives, or instantaneous messaging face fundamental obstacles. To exceed c would require bending or breaking the fabric of spacetime itself, not merely pushing harder or adding more energy. Any signal traveling faster than c would outrun its own cause, breaking the light cone structure and creating contradictions in causality. This isn't just a technical challenge, it is a law of physics. C is the ceiling on what the universe allows, governing the ultimate speed at which all interactions, processes, and information transfer can occur. The universality of c also explains the link between mass, energy, and acceleration. No matter how much energy you supply, a particle with mass cannot surpass c, because doing so would violate the causal and energetic rules embedded in space-time. Massless particles, like photons, travel at c naturally, providing a real-world illustration of the limit, but the underlying principle applies to all matter and energy. Thus, the speed of light is not a property of light alone. It is the speed at which the universe itself allows causal influence to propagate. It is the ultimate regulator of the cosmos, defining the fastest pathways through spacetime, ensuring causality, and providing the bedrock for the consistent laws of physics. Everything that moves, interacts, or conveys information is constrained by this fundamental boundary. C is the universe's way of enforcing order, consistency, and the continuity of cause and effect. From this perspective, photons are merely the messengers that travel at c, but the true significance lies in the deeper principle. C is the ultimate speed at which information, energy, and causality can operate, making it the foundation of all motion and interaction in the universe. Understanding this principle naturally opens the door to questions about hypothetical exceptions and imaginative ideas that stretch beyond our current physics, which brings us to tachyons and other speculative faster-than-light particles. Once we recognize that c is the ultimate speed limit for information, matter, and energy, it's natural to wonder whether anything could somehow bypass this barrier. This curiosity has given rise to the idea of tachyons, hypothetical particles that, in theory, travel faster than light. The name tachyon comes from the Greek word tachys, meaning swift. Tachyons are intriguing because, if they existed, they would defy our intuitive understanding of motion, time, and causality. Yet, despite decades of speculation, they remain entirely theoretical, and for very good reasons grounded in physics. Tachyons are imagined to have an unusual property: they would always travel faster than light and could never slow down to or below c. Unlike ordinary particles, which require ever-increasing energy to approach light speed, tachyons would require infinite energy to slow down to c. This inversion of the relativistic rules creates a bizarre situation. While ordinary matter asymptotically approaches c from below, tachyons would always exist above it, fundamentally separating them from the familiar world of mass-bearing particles. Mathematically, tachyons emerge as possible solutions in certain relativistic equations. If we plug in a negative value for the squared mass in the energy-momentum relation, we find solutions corresponding to speeds exceeding c. However, these solutions come with a host of problems. For one, they would violate causality. A tachyon could, in some reference frames, arrive at a destination before it was emitted, leading to contradictions in cause and effect sequences. Exactly the same paradoxes we discussed earlier regarding information transfer. Any particle or signal moving faster than light could, theoretically, send messages back in time, undermining the logical structure of reality. Another reason tachyons remain speculative is that they have never been observed. High-energy physics experiments, particle accelerators, and astrophysical observations have all tested the fundamental limits of particle behavior with incredible precision. No evidence of tachyonic particles has been found. If tachyons existed, they would interact in ways detectable by modern instruments, producing anomalous effects such as negative energy signatures or violations of standard conservation laws. To date, no such phenomena have been reliably observed. Even in theoretical contexts, tachyons introduce difficulties. Their hypothetical existence suggests that the vacuum could be unstable. In certain quantum field theories, a tachyonic mass indicates instability in the system, leading to spontaneous transitions to lower energy states. While this has interesting implications in particle physics and cosmology, sometimes used to describe phase transitions in the early universe, it does not mean that real faster-than-light particles exist. Instead, the mathematics of tachyons often signals the need to revise or reinterpret a theory rather than predict actual superluminal motion. Tachyons also force us to confront deeper paradoxes. If a tachyon could carry information, it could theoretically be used to send messages backward in time. Consider two observers moving relative to each other. A tachyon sent from one could arrive before it was emitted according to the other's frame. This violates the fundamental principle of causality, which is deeply embedded in both special and general relativity. Allowing tachyons to exist in our universe would unravel the very fabric of predictable physics, making the universe logically inconsistent. Interestingly, tachyons remain popular in science fiction and speculative physics because they offer a tantalizing what-if. They represent a hypothetical loophole around the cosmic speed limit, a way to imagine faster-than-light travel, communication, or even time manipulation. In fiction, tachyons are often invoked to explain instantaneous transmissions across light years or exotic propulsion schemes. But in the rigorous framework of physics, these remain imaginative constructs, not physical realities. It's worth noting that the study of tachyons has had some positive influence on theoretical physics. Their consideration forces physicists to clarify the role of mass, energy, and causality, and to carefully define the conditions under which theories remain consistent. In some cases, tachyonic solutions in field theories highlight instabilities that lead to meaningful predictions about symmetry breaking, phase transitions, or particle decay, without implying real faster-than-light travel. Ultimately, tachyons highlight a fundamental point: the universe strictly enforces the speed limit set by c. Any hypothetical particle moving faster than light would violate causality, require impossible energy conditions, and contradict every observation we have about the cosmos. While they stimulate the imagination and provide a useful mathematical tool in some theoretical contexts, tachyons remain purely speculative and have no experimental evidence to support their existence. This leads naturally into another avenue of speculation and imagination: concepts like warp drives and wormholes, which don't accelerate objects past c in the traditional sense but instead manipulate the fabric of spacetime itself. These ideas explore whether it is possible to bypass the light speed limit in ways that don't violate relativity directly. Once we've explored the strict speed limit of c and the speculative concept of tachyons, it's natural to turn to the more imaginative ideas of warp drives and wormholes, concepts popularized by science fiction but rooted, in some sense, in real physics. Unlike a rocket, which must move through space, these ideas involve manipulating space itself. Instead of trying to push an object faster than light, they propose bending, stretching, or folding spacetime so that effective travel between 2 points could occur in less time than light would take to traverse the same distance, but without locally exceeding c. A warp drive, inspired by theoretical physics and made famous by Star Trek, operates on the principle of contracting space in front of a ship and expanding space behind it. The ship itself sits in a bubble of flat spacetime, experiencing no acceleration in its local frame. In this way, the bubble moves through spacetime, carrying the ship along. Locally, within the bubble, nothing exceeds the speed of light. The ship isn't moving faster than c relative to the surrounding space. Yet from an outside perspective, it appears to traverse enormous distances in extremely short times. This clever concept sidesteps the relativistic energy barrier for massive objects, but creating such a warp bubble would require exotic forms of matter and energy that have not been observed, specifically negative energy densities or exotic matter capable of bending spacetime in the required manner. Wormholes present another fascinating possibility. They are hypothetical tunnels connecting two distant points in spacetime, forming shortcuts through the cosmic landscape. If stable, traversable wormholes existed, a traveler could enter one end and emerge somewhere else almost instantaneously relative to outside observers. Here again, the traveler doesn't locally exceed light speed. Locally, physics obeys relativity perfectly. The apparent faster-than-light journey occurs because spacetime itself is warped, reducing the path length between distant points. Wormholes remain speculative, as they would require forms of matter that violate energy conditions in general relativity, and no natural or artificial wormhole has ever been observed. Both warp drives and wormholes highlight a key nuance. Relativity forbids objects from exceeding light speed in their local frames, but it does not forbid the geometry of spacetime itself from being manipulated. This subtle distinction is why science fiction can imagine interstellar travel across vast distances in practical timeframes without technically breaking the laws of physics. It also underscores how deeply the speed of light constrains conventional motion. While we cannot accelerate a ship past c, clever manipulation of spacetime might allow us to travel distances faster than light would take through normal space. The challenges, however, are enormous. Theoretical analyses suggest that stabilizing a warp bubble or a traversable wormhole could require energy densities exceeding the mass of entire stars, or precise control over negative energy, conditions far beyond any current or foreseeable technology. Additionally, even if such structures could exist, they might introduce serious problems with causality. Some solutions in general relativity show that manipulating spacetime could create closed time-like curves, effectively allowing time travel and reintroducing paradoxes. So, while warp drives and wormholes are tantalizing, they remain firmly in the realm of speculative physics. These concepts also emphasize a profound point about the nature of c. The speed of light remains the ultimate local speed limit. Warp drives and wormholes do not violate this principle. They work around it by bending the fabric of spacetime itself. In other words, the universe's speed limit is absolute for objects moving through space, but clever spacetime geometry can, in principle, produce effects that look like superluminal travel from an external perspective. This distinction keeps relativity intact while inspiring ideas for long-distance travel and cosmic exploration. These imaginative possibilities serve as a bridge between strict physical law and speculative exploration, showing that the speed of light is a hard constraint on motion through spacetime but not necessarily a barrier to reimagining travel on a cosmic scale. They highlight the interplay between theoretical physics and human imagination, where understanding the fundamentals of relativity sparks ideas that extend far beyond everyday experience. From these speculative ideas, we can return to the solid ground of empirical science. While tachyons, warp drives, and wormholes remain theoretical or fantastical, countless experiments have confirmed relativity and the speed of light as a limit in real-world conditions. Observations and experiments, from particle accelerators to global positioning systems, provide undeniable proof that c is indeed the cosmic speed limit. After exploring the imaginative possibilities of warp drives and wormholes, it's grounding to return to reality. The universe consistently enforces the speed of light limit, and this is confirmed through countless experiments. The predictions of relativity aren't just abstract mathematics, they are repeatedly verified in laboratories, in high-precision technologies, and in observations of the cosmos. These confirmations give us solid evidence that c is indeed the ultimate speed limit and that relativistic effects, such as time dilation and length contraction, are real, measurable phenomena. One of the clearest confirmations comes from particle accelerators. In facilities like the Large Hadron Collider, LHC, or Fermilab, particles are accelerated to speeds approaching the speed of light. As we discussed earlier, the relativistic mass of these particles increases dramatically as they near c, and this increase is directly measurable. To accelerate protons to 99.9999991% of the speed of light requires enormous amounts of energy, and the particles never actually reach c, no matter how much energy is supplied. This behavior aligns perfectly with Einstein's predictions. The very design of particle accelerators depends on these relativistic corrections. Ignoring them would make the machines fail to control the particles, miscalculate trajectories, or incorrectly predict collision outcomes. The precise success of these experiments is a direct, empirical confirmation that relativity works exactly as theorized. Another striking example comes from muon decay in the atmosphere. Muons are unstable particles produced when cosmic rays strike Earth's upper atmosphere. They have a very short lifespan, just a couple of microseconds in their rest frame, but many of them reach the Earth's surface. How is this possible? Because these muons travel at speeds close to c, time dilation dramatically slows their decay relative to our frame on the ground. Experiments measuring muon flux at different altitudes match the predictions of special relativity with astonishing precision, confirming that moving clocks truly run slower and that relativistic effects are not mere theoretical constructs. Relativity is also critical for the functioning of GPS satellites, a technology used by billions of people every day. Satellites orbit Earth at high velocities and experience weaker gravitational fields than the surface. Both effects, special relativity, due to speed, and general relativity, due to gravity, cause satellite clocks to run at different rates than clocks on Earth. Without accounting for these effects, GPS calculations would drift by about 10 kilometers per day. Engineers incorporate these relativistic corrections, and the system works with meter-level precision. This is not abstract science. It's applied relativity that keeps our navigation systems accurate. Experiments with atomic clocks on high-speed aircraft also confirm time dilation. In a famous 1971 experiment called the Hayfel-Keating experiment, atomic clocks were flown around the world on commercial jets and compared with clocks that remained stationary on the ground. The moving clocks lost a small but measurable amount of time, precisely matching predictions from special relativity. This demonstrates that even relatively modest speeds, when combined with high-precision measurement, reveal the time-warping effects of motion near light speed. Further confirmation comes from high-energy astrophysics. Observations of cosmic rays, gamma-ray bursts, and light from distant stars confirm that all massless particles travel at sea in a vacuum and that signals cannot propagate faster. Experiments measuring the speed of neutrinos, for instance, initially raised speculation about faster-than-light travel, but subsequent measurements confirmed that they also respect the c limit. These cosmic-scale experiments reinforce that the speed of light is not merely a local phenomenon but a universal constraint. Even in everyday phenomena, the principles of relativity manifest subtly. Electromagnetic theory, derived from Maxwell's equations, predicts that light propagates at a fixed speed regardless of the motion of the source. This prediction was confirmed experimentally in the 19th century and later became one of the foundations upon which Einstein built special relativity. Every modern electronic system, from wireless communication to optical fiber networks, relies on the invariance of c to function correctly. In all these cases, particle accelerators, cosmic rays, GPS, atomic clocks, and laboratory experiments, the results consistently align with Einstein's theory. No experiment has ever found a massive particle exceeding c or a signal that breaks causality. The universe behaves as if the speed of light is an absolute boundary, both for matter and for information. These confirmations are why physicists are confident that c is more than a theoretical limit. It is a cornerstone of reality itself. This experimental evidence also helps dispel common misconceptions. For instance, some might think that rockets could just push harder to surpass light speed, or that light is fast simply because it is light and therefore special. Experiments show conclusively that the speed limit applies universally, independent of mass, particle type, or propulsion method. Light is special because it is massless, but c constrains everything, not just photons. The overwhelming weight of experimental confirmation allows us to appreciate that the speed of light shapes both cosmic phenomena and everyday technology. From the behavior of subatomic particles to the precision of satellite navigation, relativity is not just a theory, it is a practical, measurable, and universal rule. Understanding these confirmations sets the stage for clarifying common misconceptions about light speed and relativity, which often arise from intuitive but incorrect interpretations of physics. Recognizing these misconceptions helps illuminate the deeper significance of the cosmic speed limit. Despite the rigorous experimental confirmations of relativity, many misconceptions about the speed of light and the ultimate speed limit persist, partly because our everyday experiences give us intuitions that don't apply at relativistic scales. These misunderstandings are worth addressing because they reveal just how counterintuitive the universe is when we approach the limits set by c. A pervasive myth is the idea that rockets can just push harder to go faster than light. In classical, Newtonian mechanics, it seems logical: apply more force, get more speed. That reasoning works perfectly for cars, planes, or even conventional rockets, where mass is effectively constant and speeds are far below light speed. However, relativity completely changes this picture. As a rocket accelerates towards c, its relativistic mass increases, meaning that it becomes harder and harder to accelerate further. The energy required to continue accelerating grows without bound, approaching infinity as the rocket's speed nears c. No amount of fuel or technological ingenuity can overcome this energy barrier. It is not a matter of engineering. It is a fundamental law of physics. The universe imposes c as an insurmountable boundary for all objects with mass. Another common misconception is that light is fast simply because it's light, as if its intrinsic lightness or lack of weight makes it special. While photons do indeed have no rest mass, this explanation misses the deeper reason they travel at c. The speed of light is not a property of photons alone. It is a fundamental feature of spacetime. Any massless particle or disturbance in a vacuum, such as gravitational waves, also moves at this speed. Light happens to be the most familiar massless particle, which is why its speed became the standard measure. But the true significance of c is that it represents the maximum rate at which information or influence can propagate. It is baked into the geometry of spacetime itself, independent of the particle. A related misconception is that relativity only matters at extreme speeds, so we can ignore it in everyday life. While it's true that relativistic effects are negligible for objects moving at walking pace, they are nonetheless real and measurable in numerous technologies. GPS satellites, for instance, rely on relativistic corrections to function correctly. Even tiny discrepancies in the timing of satellite clocks, if left uncorrected, would cause positioning errors of kilometers each day. This shows that relativistic principles, although subtle, have practical consequences in everyday applications. Some people also imagine that time dilation and length contraction are merely illusions, as if they are tricks of the observer's perception rather than real physical effects. In fact, these effects are measurable and objective. Particle accelerators, cosmic rays, and atomic clock experiments all demonstrate that moving clocks literally run slower and lengths literally contract along the direction of motion. These are not illusions, they are intrinsic properties of spacetime, observed consistently across frames of reference. Another misconception is the idea that faster-than-light travel is just around the corner with better technology. While advanced propulsion methods or creative engineering can dramatically increase speeds, they cannot bypass the fundamental constraints of relativity. The infinite energy barrier, relativistic mass increase, and causality constraints make superluminal travel impossible for massive objects. The universe's speed limit is a physical law, not a technological limitation. Concepts like warp drives or wormholes are interesting thought experiments, but even they do not violate C locally. They work around the limit by manipulating spacetime rather than exceeding it. Finally, many assume that light speed is the fastest simply because that's how we define it, and that speed limits in physics are arbitrary human conventions. This is not the case. The constancy of C is deeply embedded in the fabric of reality. It governs not only motion but also energy, momentum, and causality. Changing C would fundamentally alter the universe, affecting everything from the formation of galaxies to the functioning of atoms. It is not a convention but a universal property verified by countless experiments. Clarifying these misconceptions allows us to see that the speed of light is far more than a quirky number or a feature of photons. It is the ultimate speed limit, a boundary imposed by the structure of spacetime, energy, and causality. Understanding why these myths are incorrect also deepens our appreciation for how the universe operates. Even seemingly counterintuitive principles like time dilation, mass increase, and infinite energy barriers are necessary consequences of a coherent, consistent cosmic framework. This naturally leads us to consider why this cosmic speed limit matters on a broader scale, not just for particles or hypothetical rockets, but for the evolution of the universe and the technologies we rely on every day. Understanding why the speed of light is the ultimate speed limit is not just an academic exercise. It profoundly shapes the universe on every scale, from the evolution of galaxies to the technologies we use in our daily lives. This cosmic speed limit is a guiding principle that governs how energy, matter, and information move through space-time, creating order and structure in a universe that could otherwise be chaotic. On the cosmic scale, the speed of light determines how the universe evolves and how events unfold across vast distances. The formation of galaxies, stars, and planetary systems depends on interactions that propagate at or below C. Gravitational waves, electromagnetic radiation, and particle interactions all obey this limit. The light from distant stars and galaxies takes years, decades, or even billions of years to reach us, meaning we see the universe not as it is now, but as it was in the past. This look-back time allows astronomers to study cosmic history, understand the life cycle of stars, and trace the expansion of the universe. Without a finite speed limit, causality would collapse, and the orderly progression of cosmic events that allows life and structure to emerge would not be possible. The speed of light also constrains cosmic communication. Signals from one region of space cannot instantaneously affect another. Instead, they travel at finite speed, enforcing a coherent cause and effect relationship. This limit determines how quickly information about supernovae, gamma-ray bursts, or other astronomical phenomena can propagate. It also defines the horizons of the observable universe. There are regions so far away that their light has not yet reached us, and may never do so if cosmic expansion outpaces light travel. In essence, C shapes the very boundaries of what we can know about the cosmos. On a more tangible level, the speed of light underpins modern technology. Our telecommunications networks, satellite systems, and even the internet depend on signals that propagate at or near C. Fiber optic cables carry data using light pulses, and the delay in transmission is directly tied to the finite speed of these signals. GPS satellites rely on relativistic corrections to account for the combination of their high velocities and weaker gravitational field relative to Earth. Without accounting for the finite speed of light and its relativistic consequences, the system would drift by kilometers each day, rendering navigation unreliable. In this way, the universal speed limit directly affects practical, everyday life. The speed of light also imposes constraints on space travel and our ambitions to explore the galaxy. Even if we develop the most advanced propulsion systems imaginable, no conventional rocket can surpass C, meaning interstellar travel requires either generational ships, relativistic time dilation, or speculative methods like warp drives or wormholes. The finite speed of light ensures that exploring or communicating across interstellar distances remains a monumental challenge, and it shapes our strategies for space exploration and communication with distant probes. Furthermore, the fundamental interactions in nature, electromagnetic, gravitational, strong nuclear, and weak nuclear forces, are all mediated at or below C. This ensures that events in one location influence other regions of space in a consistent and predictable manner. The stability of atoms, the propagation of light and heat, and the dynamics of celestial bodies all rely on the universal speed limit. If c were different, chemical reactions, star formation, and the evolution of life itself could be radically altered. Even the laws of physics, as we know them, hinge on c. Special relativity links space and time, mass and energy, and sets the stage for general relativity's understanding of gravity as curvature of spacetime. These principles are not just theoretical, they determine how particles interact in accelerators, how electromagnetic fields behave, and even how clocks tick. By shaping the fundamental rules of the universe, the speed of light enforces a consistent, predictable framework that allows both life and science to exist. In short, the cosmic speed limit matters because it defines the structure and evolution of the universe, from the smallest particle to the largest galaxy. It regulates causality, constrains communication, governs the behavior of energy and matter, and enables technologies that we depend on every day. It is not merely an abstract principle. It is the backbone of reality, a guiding limit that makes the universe coherent, navigable, and understandable. With this understanding, it becomes clear that the speed of light is not just a number to marvel at. It is a principle that underpins everything we see, experience, and create. From the earliest moments of the Big Bang to the functioning of our smartphones, c shapes the possibilities and limitations of the cosmos. This perspective naturally leads to the final reflection, seeing the speed of light not as a limit to be broken, but as a foundation of the universe, the principle around which all physical laws revolve. Reflecting on everything we've explored, from the nature of photons to the impossibility of riding light, from tachyons and warp drives to the everyday confirmations in technology and experiments, a profound insight emerges. The speed of light, c, is far more than a mere speed limit. It is the foundation of the universe, woven into the fabric of space-time, energy, matter, and information. Understanding this transforms how we see reality itself, revealing a cosmos governed by precise, elegant laws that connect the very small to the unimaginably vast. The speed of light is the universal yardstick against which the motion of all objects is measured. It dictates the behavior of particles, the propagation of forces, and the unfolding of events. It enforces causality, ensuring that cause precedes effect and that the universe evolves in a consistent, predictable manner. Without c, the notion of time would lose meaning, spatial relationships would become undefined, and the delicate web of interactions that make up reality could unravel. In this sense, light speed is not an arbitrary figure. It is a reflection of the deepest symmetries and constraints of nature. From the standpoint of matter and energy, the speed of light defines the ultimate boundary. Massive objects cannot reach or exceed it because of the infinite energy requirements and relativistic mass increases. Massless particles, like photons, naturally move at this limit, demonstrating the separation between the world of mass and the world of light speed carriers. Special relativity shows us that c is more than a physical constraint. It is a structural principle linking space, time, and energy. E equals mc squared, the equivalence of mass and energy, itself relies on c as the conversion factor that shapes the balance of the universe. From a cosmic perspective, the speed of light sets the stage for the evolution of galaxies, stars, and planetary systems. It defines the horizons of observation, letting us see the universe not as it is now, but as it once was, billions of years ago. It constrains the flow of information across space, making causality meaningful and the cosmos comprehensible. The finite speed of light also shapes our dreams of interstellar travel, forcing us to confront the vastness of space and the ingenuity required to bridge it. Even speculative ideas like warp drives and wormholes must respect c locally, revealing that the universe's speed limit is absolute, even in the realm of imagination. In our daily lives, c is no less important. GPS satellites, telecommunications networks, and high-energy particle experiments all depend on the principles of relativity and the constancy of the speed of light. Time dilation, length, contraction, and the behavior of light in a vacuum are not just abstract phenomena. They are practical realities that underpin technology and scientific understanding. C shapes both the cosmos and our immediate experience of it, connecting the grand scale of stars to the minutiae of human engineering. Even the challenges of imagining faster-than-light travel, the hypothetical tachyons, and exotic space-time geometries all serve to highlight the elegance of C as a cosmic regulator. The speed of light is a barrier, yes, but it is also a guiding principle that ensures the universe functions coherently, predictably, and beautifully. It enforces the rules while allowing creativity and complexity within those boundaries. In the end, seeing the speed of light in this way transforms our perspective on reality. It is not merely a limitation to frustrate ambitious travelers or a number to memorize in a physics textbook. It is a fundamental property of existence, a cornerstone on which all physical laws are built. From the tiniest particle interactions to the grand sweep of cosmic evolution, from the tick of a GPS satellite's clock to the light streaming from distant galaxies, C is the rhythm of the universe, the boundary and framework within which all motion, energy, and information unfold. The speed of light is the universe's way of telling us that there is an order to everything, a structure to time and space, a consistency that allows life, understanding, and exploration to exist. Appreciating this truth is to recognize that physics is not just a set of equations, but a window into the very principles that make the cosmos intelligible. C is not a limit to be broken, it is the foundation of reality itself, the ultimate measure that governs all motion, energy, and causality, from the subatomic to the cosmic. Understanding C gives us both humility and awe, humility in realizing the boundaries imposed by nature, and awe in appreciating the elegant, intricate framework that allows the universe to exist as it does. The speed of light is the cosmic metronome, the invisible rulebook, and the guiding principle that ensures the universe functions with coherence, order, and beauty. It is, in the truest sense, the foundation of everything. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.